¿Será que no me costó? Hay unos juegos que se consiguen gratuitos prácticamente. Pero el que se necesita es el de Cream.
El PSNN.
Que ese es el que hace esta forma.
Coge todo el peso.
Buenos días.
Buenos días.
Welcome to day 3. So now I will talk about liquefaction use building sediment. This is something that is a difficult problem. I've been working on it for nearly 2 decades. And students like Roberto Luque, Sinead Ashby, Rodolfo Sancio, and others have been critical in terms of moving the ball forward. It takes a lot of very good students to do some good work. But Jorge Macedo, who's now a professor, assistant professor at Georgia Tech, was really instrumental in doing this work. The 1999 Kojali earthquake was really the start of my journey of understanding how buildings on shallow foundations respond to earthquakes. Like I'd say, most of my best research has resulted from observations in the field that I haven't understood. So I strongly encourage you that when there is a disaster, it is a terrible thing, but it's more terrible if you do not learn from it. So please organize and go out in a responsible, respectful manner to collect the perishable data, see things that will shock you and make you curious and make you develop additional skills in earthquake engineering. Also, when a client pushes you to shave away some conservatism, because that rare earthquake's never going to happen, seeing the death and destruction brings you back and says, no, I can't do that. Christchurch is another example. Different infrastructure, buildings sliding, tilting, punching into liquefiable material. One of the best examples is in the 2010 Chile earthquake, where a structural engineer said, you have got to go to this city. There's liquefaction that has shut down a modern hospital. This regional hospital shown here to the left was built to be there when the earthquake occurred. The only place in this region where there was liquefaction was where this tall, heavy building exerted loads into the soil. The street and the light one-story buildings in the town did not have enough inertia, enough load to generate the liquefaction. Structural engineers say liquefaction is bad for the building. Buildings are bad for the ground. If we don't build any buildings, the world's a lot safer. You can see that in the centrifuge tests that I conducted with Sinead Ashby, where the building basically wiggles its way in to the soil. Watch it one more time. That's SSI ratcheting. And then we talked at the end of yesterday about the fact that what the owner of this building cares about is what's most damaging in terms of the access to the building, the pipes coming in and out of the building, is the fact that it has pushed 400 millimeters into the surrounding soil. It's also important that the surrounding soil has undergone volumetric settlement, and so the total settlement is 700 millimeters. So there are 3 displacement mechanisms that I like to consider. The obvious one, the most difficult one, but the most obvious one, is if I've got 15 centimeters of sand beneath my foundation and ejecta forms and that sand is now on the ground surface, I clearly have mined out soil and I'm going to get settlement because of that ejecta process. I like to look at shear-induced deformations 2 ways. If I could base isolate the building, when the ground softens, because now it's softer, the building which was supported on that ground when it was stiff with the high effective stresses, with the low effective stresses, the building now pushes into the soil. If I could push a cone in the soil during liquefaction, I would measure low tip resistances, and I would say, oh, that's a bearing capacity settlement. We also have the SSI ratcheting, which is a function of the mass and the inertial response of the building. The building does one of the most cruel things it can do to the soil. It puts the soil into tension right before it hits it on the head. That's a very effective way of having a building work its way down into the soil. And you, of course, get volumetric deformations. Because of the high transient excess pore pressures leading to differential hydraulic heads across the system, and Darcy's law is working, water is moving from one part to the other. Typically, the hydraulic head at a certain elevation is higher in the building than it is in the free field, so water tends to move out from underneath the building. So you are getting some drainage to occur during strong shaking. When you get sedimentation, that leads to significant settlement, and then post-liquefaction reconsolidation leads to settlement. A building case history that's very informative is the case of the CTUC building in the Christchurch earthquake. It was also excited by the Dartfield and June events. We went into the garage, and with a laser level, we were able to measure settlement. We saw that this building punched down relative to the lighter building next to it, 60 millimeters. And there was a little bit of differential settlement, but most of the differential settlement, 200 millimeters of it, occurred over the last two bays of the structure. The bays were about 4.5 meters wide. That's because of the buried stream channel that we'll talk about that cuts across it. With those measurements and knowing how much ejector we get on the south side, but none on the north side, we are able to look at different mechanisms. How much settlement we got approximately because of ejecta. We know the rest of the differential is due to the shear-induced component. And then we have a ridge on piles that's not too far away, and so we're able to look at the free field settlement as well as what we calculate to estimate that. So we have an estimated total settlement on the south side and the north side, but more importantly, for refining our insights, we can break these settlements down by these different components. The owner of the building shared the foundation plans, shared the structural plans. So now, knowing we have these observations and knowing we have the plans, we now invest in doing our site investigation. This is a cross-section through the building from the south side to the north side. The building footprint is right here. We did CPTs around the building, such as 5 and 7, a few other ones, 10. And the great thing about the CPTs, we're looking at the data and we realize we need to add a CPT because the ground conditions on the south side in CPT Z45 are very different in the shallow region than Z47. So midway through the length of the building, we put in another CPT, number 28, at the Zone 4 project site, and it shows that it does not have the buried stream channel. So that's why we don't see much settlement in this region, and we see a lot more settlement over the last two bays. It's because it's over that liquefiable material. Shouldn't be a shock, because again, as I showed you yesterday, this is an area where there was mapped some shallow stream channels that were buried when they developed the city. The model needs to be able to capture that. And so it needs to be able to capture this loose, silty sand and low plasticity silty soil with a relative density of 40% using several different correlations from the cone. And there are greater thicknesses of liquefiable material at depth below the north side of the building, and we capture these things. We use PM4 sand version 3 that was developed by Ross Boulanger and Caterina Ziotullo, and we calibrate that against laboratory testing done by Chris Markham so that we can go beyond just the 3 parameters that you have to select to use that model. So the importance of field and laboratory testing is important. Roberto Luque did this analysis based on the work of Chris Markham, based on the work of Josh Zupan, based on the work of Ross and Katerina. It takes a village. The insights you get from this are very important. So this is the south-north side. South's in red, north's in blue. What you care most about is settlement. You can see the settlement of the northeast corner of the building versus the settlement of the southeast part of the building. Most of the settlements occurring during strong shaking. The differential settlement is shown here in terms of red. This is the calculated settlement. Of course, we don't know the properties exactly, so we did a sensitivity analysis, so that's the range. And the best estimate of just the shear component is shown here. We should not be able to match what was observed in the field exactly. In fact, our analysis would be wrong if we matched the field observations exactly, because our continuum-based analysis cannot capture ejecta. So if your analysis should not be able to capture ejecta, you don't want to get the right answer. You want to admit that you cannot capture that mechanism. You can capture shear, capture volumetric, and then you have to add in the amount due to ejecta. You can see the strains under the building versus the strains in the free field. So the building is obviously causing more strains in that salted material. One of the more informative things is to look at deformation mechanisms. So here's another building that I'll just quickly go over. The fact that it matches what was observed is nice, but more importantly is the insight. What we see here is if we look at the west side in yellow and the east side in magenta, when the east side is moving up, the west side is moving down. The edges of the building on this map, on the individual spread footing foundation is basically rocking down, and as it's going down, the edges are going down more, so it's hogging. It's getting a deformation pattern like that. You're seeing that because the center of the building is not settling as much as the corners, which are working their way in to the ground. So this is not a bearing capacity type failure with ejecta. This is SSI ratcheting, because it's a heavier building that is responding in that way. So key insights from this work that was done by several of PhD students, including Roberto Luque, is liquefaction-induced building settlement is caused by ejecta, shear, and volumetric mechanisms. It's insightful to look at it that way, because sometimes you don't have ejecta. You have a thick crust, and you can take that out. And we have ways of estimating volumetric settlement. We talked about those yesterday for free field cases. Now we just have to focus on shear. The 1D post-liquefaction and reconsolidation settlement of Zhang et al. 2002 only captures volumetric. You need to do nonlinear, dynamic, SSI, effective stress analysis to capture the shear-induced building settlement. So just fire up FLAC and PM4 SAN, and for every project you have, do that advanced analysis. Why don't I get a really smart PhD student to do a lot of analysis with a 2D FLAC program with PM4 SAN for variable conditions, and then share those results with you, so at least if you're going to do that analysis, you know what the answer is before you do the calculation. Or if you don't have the budget to do it, you can say, well, my building is like the buildings that Jorge Macedo evaluated, and we can build on those. I'm deliberately not doing a 3D analysis, and I feel very strongly about this. It is state-of-the-art to do a 2D, nonlinear effective stress analysis, SSI of a building. You typically don't have enough ground investigations to really characterize the hydraulic connectivity and all the things that are important in 3D. So I'm thinking that most of the time, if you're going to do an analysis, it's going to be 2D. So I'm going to do 2D analysis so that we have consistency between what I'm calculating and what you might calculate. So this is what Jorge did. He used this model and he looked at 105 possible models. This is the baseline model, which has a typical building with 3 modes. So we captured 3 modes. It has the right mass to get 80 kilopascals on a mat foundation, about the right height and width for some typical buildings. We're going to mainly look at 2 to 8-story buildings. We have a non-liquefiable crust of 2 meters, a liquefiable material of 3 meters with a relative density of 50%, and then we have some denser soils that don't liquefy, but they generate pore pressure, and then our compliant base. And we're going to vary the relative density of the liquefiable layer, the thickness of the liquefiable layer, the thickness of the crust, the width of the building, height of the building pressure. We're going to run through all those things. And then we know the ground motion is important. So we're going to run 12 baseline motions that I have enough experience to realize that it push the building in certain ways. Pulse motions, long duration motions from subduction zones, a number of different cases. And then we're going to add in 24 more to make sure that we're getting a good, best estimate of the median response. First thing to look at for this baseline case of a 3-meter thick soil that can liquefy with a relative density of 50% for 1 ground motion, only 1 ground motion, you can see the shear mechanism developing in the liquefiable layer. What's also informative is to look at this plot, which shows in red shear and in blue volumetric strains calculated by the program. The dotted line are 15 seconds into strong shaking. That's when you're in the maximum shaking level. And then the blue and red volumetric and shear are at the end of strong shaking at 46 seconds. What you see is largely during strong shaking is the shear mechanism that governs. The volumetric is a small part of the whole thing. Even at the end of ground shaking, it's the shear component that dominates. So it's not an oversimplification. It's reasonable to just say we're getting shear primarily during strong shaking. We're getting volumetric after strong shaking. I like the Schmertman CPT approach for doing static analysis. I like the idea of the Schmertman triangle. So I said, why don't I just modify that method? Very quickly I realized this is a dynamic problem, and just as Professor Kramer showed, how the strains develop in the layer have to do a lot with the ground motion and initial response and the phasing. It's not going to be as simple as a static analysis and making an adjustment to the Schmertman CPT static settlement method. We looked at different ground motion parameters. This is a subset of all the ground motion parameters we're looking at. We want to find that one ground motion parameter that estimates settlement best in terms of having the lowest standard error, plus being sufficient so it captures everything. There's no bias in the residual. The 3 that kind of jump out are cumulative absolute velocity, Arius intensity, and spectral acceleration at 1 second. We deliberately picked ones that we thought would not work. You don't want to just pick the ones you think might work. You want to pick ones that you think should not work well, so that you can confirm that, yes, I understand that duration by itself should not capture this whole problem. This is 1 ground motion, just to provide some insight. This is the acceleration time history. You can see the excess pore pressures that develop under the building in black versus those in the free field because of the extra confinement and load you have from the building. So you're going to expect water to move out from under the building, so that is a consideration. What you care most about, what your owner of the building cares about, is settlement. So this is the settlement versus time movement. When Shade had first showed me these kind of plots from the centrifuge test, I said, that looks a lot like a Husik plot. So we focused on Arius intensity. I wanted to look at some additional things, and we actually said the best relationship was cumulative absolute velocity, slightly better than Arius intensity. And I overlapped the percentage of the cumulative absolute velocity on top of this to showing that it's mimicking nicely the shear component. Of course, when the shaking stops, it's done. and we're getting post-liquefaction reconsolidation sediment that will continue to go on. But for just capturing the shear component, cumulative absolute velocity works well. So we looked at cumulative absolute velocity. This is just the baseline motions versus settlement. It tracks nicely, but it wasn't sufficient. There was still a bias in the prediction, so we added in spectral acceleration at a period of 1 second. That's a reasonable value because most site profiles that are subject to liquefaction or May liquefaction, they don't have site periods of 0. They have site periods closer to 1 second. And so this is more meaningful to PGA. That's the influence of the earthquake shaking. Now let's look at the influence of the building. It should not shock you that as the building contact pressure increases, these are 12 baseline ground motions. Less intense ground motions, moderate and very intense ground motions. Let's focus on the very intense ground motions. And as we increase the contact pressure, settlement increases. But as we would expect, it's nonlinear. But I don't expect it to go down. Why would it go down? Then I go back and I looked at some centrifuge testing done in England, and they showed for one of their results that a heavier building suppressed the generation, didn't suppress the generation of pore pressure, it suppressed R sub U. The pore pressures were high, but as a percentage of the vertical effective stress, because the building was so heavy, was actually not as high a RU as a lighter building. And then we went back and looked at some of our centrifuge tests and those of Bruce Cutter and his students, and there were a couple of cases where a building being heavy enough caused the RUs under the building to be less than it would be with a lighter building. So I actually think this is truth, not fiction. Other people have looked at this problem, including Professor Tokamatsu from Japan, and so we suspected that as the building gets wider, as your boat gets wider, it's more stable, and you get less settlement. So building settlement goes down as building width increases. Of course, soil matters, and of the soil parameters that are most important, it has to be relative density. So again, here's 12 baseline ground motions, so we can look at the details. Let's focus on the upper strong ground motions. At 35% and 50% relative density, the soil liquefies, the building pushes into it, we get settlement. But as we'd expect, we don't get a big difference between 35 and 50% relative density because the soil is so weak, it liquefies and we get settlement. As the relative density increases, now we get a sharp drop in the amount of settlement. And by the time we get to 75% relative density, or 90, the settlements are a much smaller amount, especially for low levels of shaking. But importantly, if you shake a 90% relative density soil very hard, you'll get some building settlement because you will get some buildup of pore pressure, which will soften the soil and lead to some settlement. We know that as the thickness of the liquefiable layer increases, settlement increases, but only to a point. As the layer gets thicker, it can accommodate more of the shear mechanism. Once the layer gets very, very thick, the shear mechanism is accommodated, and adding thickness really doesn't make a big difference. I used to believe, based on this plot that I've seen by several authors, that the way to estimate building settlement is shown here in the pink area, is the average building settlement normalized by the thickness of the liquefiable layer, and given the building width normalized by that thickness gives me an indication of settlement. Building settlement being proportional to thickness of the liquefiable layer would only be true if it was all volumetric. You double the thickness, you double the volumetric strain. It's not all volumetric. These were thick deposits of layers. Shade Dashky and I actually did centrifuge tests in green in this region to show that we could get consistent results. But then we were the first to actually do centrifuge tests with relatively thin layers. And we showed that just like we saw in Adapazari, Turkey, where there was only about 1 meter and 1.5 meters of liquefiable material, if that stuff softens, it just squeezes out like toothpaste under your building and you get settlement. So do not use this relationship. And of course, as the layer thickness of the crust gets thicker, then eventually, if the crust is very, very, very thick, the seat of settlement of the building is in the crust, and there will be no shear-induced component, and the building and the ground conditions will go down the same. It'll be all volumetric. So building settlement depends on the relative density of the liquefiable layer. It depends on the thickness of the liquefiable layer to a point, and it depends on the thickness of the non-liquefiable crust. You're not going to estimate relative density for a natural soil deposit, so we need to have a way of estimating that. Well, the most robust way of getting an estimate of relative density that you can trust for a clean sand or a slightly silty sand using clean sand correction is the CPTU. If you must, you can use an SPT to get relative density, but just realize the method's not going to work as well there because the correlation between relative density and SPT is much more uncertain, and the SPT end value is much more uncertain. So try to use the CPT. Then you can also use a CPT-based method to estimate the factor of safety against liquefaction triggering. You probably would not have done this analysis unless you saw that you had layers that would have liquefied. So it's best to use a CPT-based procedure. If you must, you can use an SPT-based procedure. Each layer now is defined by its thickness, dz, the depth to the midpoint of each layer, z, the relative density you estimated in the first step, and the factor of safety against liquefaction triggering, which you analyzed in the second step. So now I have a problem where I have as many layers as you think are important that capture these 4 parameters. I'm going to go back to the work of Professor Ishihara. It's difficult to do work in this field and not follow the footsteps of Professor Kenji Ishihara and Professor H. Bolton C. In this case, his laboratory tests were then implemented by Zhang et al., and equations were developed to get shear potential. Of course, I want to focus on shear. So if the factor of safety for this layer is 0.8 and its relative density is 60%, its shear strain potential is 10%. So for every layer, I can estimate a shear strain potential. I have the shear strain potential because the liquefaction directly beneath the building is the most dangerous. I'm going to normalize by 1 over depth as my depth weighting factor. I'm going to multiply by the thickness of each layer, and W is just to ignore any soil layer that is above the base of the foundation. The foundation is defined by Q, the bearing pressure, and its width, B. We have a spreadsheet, you have a spreadsheet in your hand, in your notes, and I started developing a method for taking the CPT, converting it over, and then I realized Peter Robertson's already done that with his friend John in Greece. Why should I reinvent the wheel? They already have the Zhang et al. Procedure in CLIP. Hey Peter, can you put this method into CLIP? He goes, yeah. And then once you've done it, give us the beta version, we'll test it for all the cases, make sure you've done it right, go through a couple iterations. So now I just use the calculation of the liquefaction building settlement index that's in CLIP. I always like to start a problem, whether it's an excavation. The first thing I do is I calculate the factor of safety against base heat. If that factor of safety is low, I know I have an instability issue and maybe large deformations. Factor of safety is high, I might have deformations, but they're not going to be uncontrolled. When you look at a levee on top of a liquefiable material, the first thing you should do is say, okay, it liquefies, give it a residual strength, and calculate a post-liquefaction static factor of safety. Liam Finn did that and showed that factor of safety is high, very little deformation. Factor of safety gets low, below 0.91, 0.8, you start to get large deformations. We found a method by Meyerhoff and Hanna that was for clay, but we'll say, okay, in a simple sense, we have a shear strength, an undrained shear strength of the crust, and we have the residual strength of the liquefied material using a method like Professor Kramer talked about yesterday. And this two-layered system can calculate a post-liquefaction bearing capacity factor of safety. If you know of a three-layer system, please let me know, because this is the best we have right now is a two-layer system. But at least gives you an index. As the factor of safety reduces, the amount of deformation increases. Why do we get low factors of safety that are calculated that have low deformation? It's because we're using a two-layered system which says that this soil is infinite. That's why I want a three-layered system. And so we are missing cases of thin layers, and also we're missing some of the cases of very heavy pressures. But it's a good index. It gives us a sense of when we have large deformation potential and when it's going to be small. So the insights from this study is the shear-induced mechanism governs building sediment during strong shaking and ejecta if it occurs. You can get large building settlements if your post-liquefaction bearing capacity factor of safety is less than 1. The key earthquake motion parameters are cumulative absolute velocity and spectral acceleration at 1 second. The key building parameters are Q and B. Where's H? Shouldn't the height of the building matter? Remember, I restricted this to 2 to 8 story buildings, because I don't think you're going to do a simplified liquefaction analysis of a 22-story building. I hope you're not. Okay? And for this range, when we increase the height, Q increases. So we looked at some cases where we held one constant, and we realized that actually much of the H effect is in the Q. And for these buildings that are not as exceptionally tall, the height is not important. The minute you go above 10 stories, I've got to believe height of the building would be in the parameters. I'm happy with using my method from a 1-story building to a 10-story building. I would never use it for an 11-story building. I draw the line at 10. And then the key site parameters are relative density, thickness of the liquefiable layer, and thickness of the crust. Those can all be wrapped up in LBS, the Liquefaction Building Settlement Index. So this is the equation, which is in a spreadsheet, and more importantly, it's implemented in CLIC. So you don't have to memorize this, although you get extra points and extra credit if you do. If you know all of these things perfectly, if there is an error in estimating, or there's uncertainty in estimating this shear-induced component, so that's what the sigma's for. And then of the parameters, you can imagine cumulative absolute velocity is the most important. Spectral acceleration at 1 second is very important. Q is important. B is less important. And LBS is a really important parameter. That's the ground conditions for the most part. I said, okay, we're not ready to publish this because you only use FLAC and you only use PM4 SAM. You have to do effective stress analysis with at least 2 different models for consistency. Luckily, I didn't have to hire another PhD student because Sinead Ashley had gone to another university University of Colorado Boulder. She had hired a really good PhD student. Because she had to be different than me, she decided, I'm doing 3D analysis, I'm using OpenSeas, I'm using a mainframe computer, and I am basically using Elgamow's pressure-dependent model. So she was kind enough to share her results. We then did our results, and they match nicely. There's only a bias when the displacement is less than 5 millimeters. If she calculates 4 and I calculate 1 millimeter, that's a factor of 4, but I don't care. They're both 0, or not 0, negligible, okay? So now I go, okay, this is not biased by one model. It's consistent with at least 2 of the most well-used, validated models out there and computational platforms. But I'm not going to stop with that. I have all of these centrifuge tests that have been done by students working with me and students working with Bruce Cutter at UC Davis. And we go back and we have measurements of how these model buildings have settled in the centrifuge. We use our method to estimate it, and that's not so bad. There's no significant bias, and we're in the ballpark. The best we're going to be able to do for this very challenging problem is be within a factor of 2. Okay? If our best estimate is 100 millimeters, then realistically we tell the client 50 to 200 millimeters. And anyone who gives you a range shorter than that is probably being a bit too confident. But I'm going back to the field because analysis is analysis, and centrifuge tests, no matter how well they're done, they are a model of reality. This is reality. And this is just a few of the 19 field case histories where we looked at the shear reduced component that was observed in the field and what we estimated. And the trends are nice because this is the same building, different earthquakes. The Christchurch earthquake had large settlements. We calculate large settlement and capture things fairly well. And then for the lower intensity motions, we calculate lower displacements. You can look at this that's in the paper, that's in the materials that you were provided. When I presented this, Liam Finn was in the room and he goes, well, what about ejecta? I go, well, let me at least be happy that I've solved the shear-induced problem. Give me some time to relax in that. But then I realized practicing engineers go, well, there are some cases where we get a lot of ejecta. You've got to give us some idea of how to estimate that. What I had been saying is use field case histories and use the Ishihara plot of 1985. We're working on this with 2 students that are very good. One is Daniel Hudebrat, and he has looked at the data for clean sand sites, which we know are very different than stratified silty soil sites in Christchurch. We're looking at that parameter called liquefaction severity number, LSN, and for these thick, clean sand sites, we're seeing that if LSN is less than 10, you're not likely to get ejecta. If LSN is greater than 10, you are likely to get ejecta, but we've got some work to do because it can't distinguish between minor, moderate, and severe. At least it tells us when we have ejecta and when we don't have ejecta for these sites. The positive news for stratified silty soil sites, because of the bias in the methods, LSN now is at 25. So you have to get up to an LSN of 25 before you start to see ejecta. And these silty soil sites don't make as much ejecta, so we only had 1 or 2 cases in the database with moderate, and we had no cases with severe or extreme ejecta. So it's telling us silty soil sites can give up some ejecta, but not much. Here's an example of a site called the Shirley site, which was shaken by the September earthquake in 2010, the Christchurch earthquake, and the June earthquake. And what's highlighted in yellow, so you can see it more clearly, is the amount of ejecta. It was none for the Darfield earthquake, it was extreme for the February earthquake, and it was severe in a relative sense for the June 2011 earthquake. St. Teresa is a place that all our methods say should liquefy. In fact, LSN numbers are higher for St. Teresa than they are for Shirley. But they're a stratified silty soil site in an old swamp area. There was no damage there, so they didn't even fly over it. There was no damage there, but they decided to fly over more of the cities to look at cases where there wasn't damage. That's just as important. Don't just look at where there is damage in an earthquake. Look at where there's no damage. Because performance-based earthquake engineering requires us to have methods that can differentiate between good performance and bad performance, but no liquefaction. So, as a preliminary look at, let's take the idea and say, if eject is going to happen, we have to have artesian conditions. So we have to have the excess pore pressures generate a head that's greater than the head required to cause artesian conditions. We're going to take that head difference that would then, if you put a pipe in the ground during this liquefaction tank, you'd have water coming out of the top. Eventually there'll be a crack in the crust and the water will come out to the top. This is the driving force. We're going to square that to weight it and then times it by dz thickness. And so we have this parameter we call the ejected intensity parameter, which is in meters cubed. So it's a volume term right now. This is the analysis using open seas with PM4 sand for the Darfield earthquake, the Christchurch earthquake, and the June earthquake. This is the displacement during shaking, the displacement profile. This is the excess total head. This is the 1-to-1 line that would lead to artesian conditions in black. This is RU equal to 1.0. This is the soil profile. It's primarily PM4 sand in red. There's a little bit of PM4 silt where we've adjusted to match the silt. And then there's PM4 silt, which is really PM4 clay-like to do the clays. And hopefully this works. It doesn't. Okay. Let me try one more thing before I give up. You have a place for a USB on here? Yes, you do. This is a very big file, so it didn't work on the other computer, but maybe it'll work here. Uh-oh. We'll play it. No. Okay. I will see if I can get my computer working again, but it probably won't. If you want to come by during the break and look at it, it's a cool movie. Trust me. Let me describe. It's just too big an animal. What happens is obviously this shakes back and forth. It looks cool. This shakes back and forth more because the Christchurch earthquake is more intense. And what you see here is only a few layers liquefy. Importantly, the total head gets above the head required to cause artesian conditions. But importantly, this generates significant pore pressure. It doesn't liquefy, but it has a head higher than the head of the soils at the shallow layers. So it's constantly feeding that. So that's why these sand boils could last 5 minutes after ground shaking. We have a video. Oh. No. Okay. I got too excited there. So you actually end up finding that your ejecta intensity goes up, and even after strong shaking, it stays up, and so you have a large potential for ejecta. When we look at this site, we have areas that liquefy. This area liquefies. Some of these other layers liquefy. They get R sub U equal to 1, but they're isolated from each other. So they don't feed each other. They're not hydraulically connected. And so you never get a layer that it has sustained flow. You never really get a case where you have a total head greater than that necessary to cause artesian flow, so you don't get a lot of ejecta. You don't get any ejecta. So finishing up, let's go back to the building that Roberto Luque analyzed with a 2D effective stress analysis with flak and PM4 sand. And let's see how we do with the simplified method, which is basically regression through all of the results done by Jorge Macedo for a bunch of general conditions, which include this 6-story building. This is described in the Bray Macedo paper 2017 in Soil Dynamics and Earthquake Engineering. Number one, you do a liquefaction evaluation. You're always going to do a liquefaction evaluation at the start of things. And so we color in those areas that have, those layers that have factors of safety against liquefaction less than 1. I drew this in red because it's very loose and it's shallow. The rest of these in orange are areas that are liquefied. There's actually a greater thickness of liquefiable soil on the north side, 6 meters, compared to the south side. But we're going to learn that shallow liquefaction is more damaging than the deep liquefaction, and we're going to capture that with LBS. We then do the post-liquefaction bearing capacity factor safety calculation using that equation, a closed-form equation from Meyerhoff and Hanna, keeping things simple. The crust is estimated to have a strength of 35 kPa. And using the Idris and Boulanger 2008 relationship, we estimated a residual strength of the liquefied material of 8 kPa. Sticking that into those equations, we got a factor of safety just less than 1. So we know we're probably going to have large displacements. The ejecta-induced settlement is still a difficult thing. We're providing some guidance on that, but you still have to use a lot of engineering judgment. This is a little bit easier because I kind of know what the answer is. So to take that variable out and using what we estimated to be the settlement of the ejecta, it was 75 to 125 on the south side. It was 0 millimeters on the north side. The indicator of that is we don't expect ejecta if the LSN is less than 10, and it's 5 on the north side. And we do consider have ejecta if we have an LSN greater than 10 at a sandier site, so we basically have an indication. The other way of looking at this is with Ishihar's 1985 plot that I showed you yesterday. Then we have the volumetrically induced settlement with Zhang et al. 2002. We talked about that yesterday. That's a good method for estimating post-liquefaction volumetric settlement. We could use our computer code to do that, but actually Ras Boulanger forced PM4 sand to get the answers you would calculate with Zhang et al. Because most consistent models have a hard time estimating post-liquefaction volumetric strain for a 1D profile. So why don't we just not use the computer program and use Zhang et al. To estimate volumetric strain? We see 150 to 250 millimeters on the south side, slightly less, 100 to 200 millimeters on the north side. Now we go to the shear-induced settlement using the new method that we proposed in our paper. It's a function of the spectral acceleration at 1 second, which was estimated based on records and attenuation relationships based on those records of being about 0.9 g, pretty high. The cumulative velocity was about 1 g second. That's relatively high too. You'll get a feel for these numbers. LBS was calculated with our spreadsheet and CLIC, and we essentially get the same answer because we calibrated them against each other. It's 57 for the south side, 10 for the north side. The typical numbers are anywhere from essentially close to 0 all the way up to about 100. You'll get a sense of that as you play with it. but 57 is relatively high, 10 is moderate. Using the thickness of the liquefiable layer, which goes into the equation, using the Q. Now, this is the case where you have individual spread footings that have weak tie beams. Don't ever build a building with isolated individual spread footings in an area that might undergo ground deformation. And if you are going to take the trouble to tie your foundations together, which you should, use thick, deep grade beams. Don't use tiny little tie beams because they don't really work well. The better thing to do is not individual spread footings with big, beefy grade beams, but actually a mat. A thick, heavily reinforced mat is the best foundation for almost every ground condition, ground deformation issue I've seen. Since these are tie beams, we did it with the tie beams being effective, so 70 kPa over 20 meters, and we did it for individual spread footings where the tie beams were not effective, and we kind of used the average of those two because we weren't sure, and that's how we calculated 110 to almost 300 millimeters, and then 40 to 120 millimeters on the south and north side. As you'd expect with that shallow liquefiable soil, right under the south side, we get a lot more shear-induced deformation on the south side. Now we add them up. The south side has ejecta, volumetric, and shear. These are just the median estimate. And so on average, 480 millimeters, but that's the range, given the uncertainty. And on the north side, no ejecta settlement, a little bit of volumetric settlement, less shear, so it's 220 with that range. So what the structure engineer cares about is differential. The differential settlement is 260 millimeters. We measured 250. I do not guarantee this level of success. I'm a professor. I'm coming all the way from America, the United States of America, to impress you. This is my best case history, okay? The other ones are not so bad, but I'm going to put my best outfit on today to try to impress you. So just realize it's never going to be that good, but it's at least reasonable in giving you something to get in the ballpark. So liquefaction-induced building settlements are caused by ejecta, shear, and volumetric mechanisms. The shear-induced mechanism governs during earthquake shaking, in addition to ejecta, which you have to estimate separately. Our method can estimate the shear-induced component and the uncertainty. And most importantly, this is the bottom line, you will only use this method because it provides results that are consistent with 19 well-documented field case histories, 102 centrifuge test results, and thousands of dynamic analysis, not those just done by us, but those done by Sinead Ashley and her PhD student. This is the method, it's in the paper. Thank you very much. Thank you for letting me use your computer.
Don't need to get a beefier computer.